In this work, we demonstrate a correlative workflow for inspection and analysis of advanced semiconductor packaging. The approach combines X-ray computed tomography, ultrafast laser processing, and multi-modality microscopy to navigate from an intact consumer device all the way to deeply buried structures within the Apple A15 package. One of the major challenges in advanced package failure analysis is simply reaching the region of interest. The target layer may be buried beneath multiple mechanically complex and compositionally heterogeneous layers. Conventional destructive preparation can remove important spatial context before high-resolution analysis even begins. The small variations between nominally similar devices can also make localization difficult and lead to unnecessary rework. Our approach turns this into a controlled, verify and decide process. We begin with non-destructive CT imaging to locate the target and understand the surrounding geometry. We then plan the access route, use the laser to remove material in controlled steps, and verify the result using optical, confocal, and SEM imaging. Based on those observations, we decide whether to continue deeper, change the access direction, or perform more localized processing. The process starts with micro-CT imaging of the entire smartphone. At this stage, the objective is not yet maximum resolution. Instead, we want a holistic three-dimensional map of the device that shows the internal architecture and, most importantly, the position and orientation of the A15 package relative to the rest of the iPhone. Using this CT information as our guide, we can now open the device in a much more informed way. Rather than disassembling the phone blindly, the CT volume tells where the package is located and how it is oriented. As shown in this video, we progressively open the phone and extract A15 package while maintaining the connection between the physical sample and its original three-dimensional location within the device. Once the A15 has been extracted, we perform a second micro-CT scan, this time on the package alone. Because the field of view is now much smaller, the scan provides higher resolution information about the internal package architecture. This becomes our more detailed navigation map for the laser processing steps that follow. The isolated package is then transferred to the Tescan FemtoChisel. From this point forward, we begin controlled laser process. The first objective is decapsulation, removing the encapsulating material while exposing the package-level structures underneath. After laser-only decapsulation, we expose readable package-level features, including two DRAM-related circuitry regions and adjacent silicon structural blocks. This is an important first checkpoint. Optical imaging shows the overall geometry, while confocal microscopy provides three-dimensional topography and helps us understand the depth and uniformity of the laser removal. We then move to SEM for higher resolution inspection of the exposed DRAM regions. At this scale, we can evaluate the visibility of traces and other fine structures and determine whether the preparation quality is sufficient for further analysis. These microscopy checkpoints are critical because the laser is not simply removing material continuously. Each major removal step is followed by inspection and verification. Once the first exposed state has been documented, we continue the delayering process. Here, the upper DRAM structures are progressively removed to access the material underneath. Again, SEM is used to examine the resulting surface after this processing step. These repeated laser and microscopy cycles allow us to follow the changing structure of the package and verify that we are progressing towards the intended layer rather than relying only on a predetermined removal depth. Further delayering through the DRAM-associated silicon reveals another buried DRAM layer. This demonstrates one of the key capabilities of the workflow, progressively navigating through a complex three-dimensional package stack while retaining an understanding of where each newly exposed structure sits relative to the original CT volume. The newly exposed structures are once again investigated using FIB-SEM. This provides the high-resolution confirmation needed before we proceed deeper into the package. We then continue laser delayering beyond the DRAM-associated structures and begin exposing the interposer metallization. Here, we reach the first copper layer, transitioning from the upper package structures into the buried interconnect architecture. SEM imaging allows us to inspect the exposed copper structures and evaluate the metallization pattern at these steps before continuing further. Additional controlled laser removal exposes a second copper interposer level. The important point here is that we are not simply producing a single endpoint. We are creating a sequence of experimentally verified access states through the package. Again, the newly exposed metallization is examined by SEM to document the structure and confirm the progression through the package. Further delayering brings us to a third copper interposer layer, demonstrating continued controlled progression through multiple metallization layers. At each of these deeper levels, SEM provides the higher resolution view needed to interpret the exposed structures. Combined with the earlier computed tomography data, optical, and confocal information, these SEM images become part of a continuous multi-scale record extending from the intact smartphone to individual buried features within the package. To summarize, CT-guided laser access changes destructive sample preparation from a largely open-loop operation into a controlled, evidence-based sequence. CT reduces localization uncertainty before processing begins and preserves the three-dimensional context of the original device. High-throughput laser processing then provides rapid access through the package, while optical, confocal, and SEM checkpoints verify each important stage. The result is a workflow that connects device-scale navigation with microscopic interpretation of deeply buried structures. This approach can reduce rework, improve reproducibility, and provide a scalable pathway for advanced package failure analysis, reliability studies, and security-oriented inspection.